Okay. I think my audio was dead on the previous stream there. Anyways, yeah, let's continue reading here. Actually, no, I'll just full screen this guy here since I'm not doing any coding. Okay, I was just covering this two's complement stuff. The terms, okay, so let's, it's all derivation stuff. I hate reading these derivation things. All right, well, let's look through the math and make sure we understand it. So we're defining addition of two's complement of a w width integer, bit width integers between two integers x and y. And the addition is just basically converted to an unsigned bit vectors, add those bit vectors together, and then you convert that back to a two's complement number. And if you do the substitution in there, it comes out to this expression, which is simplified into just being x plus y mod 2 to the w. Okay. The terms x w1 2 to the w and y w1 2 to the w drop out since they equal 0 modulo 2 to the w. To better understand this quantity, let us define z as an integer sum. The value z prime prime is equal to that. We can define the analysis for our four cases as illustrated below. I'm not gonna, I'm gonna start skipping some of these derivations because they're just so laborious and they provide so little value to my insight. So this is gonna be skipped. I will not skip the problems because I think that practice problems and homework problems really demonstrate your understanding. They're really where the meat is. Laboring over derivations of a mathematician who just really likes their math isn't something I feel like I'll get much value out of. So I'm going to start skipping those. Two's complement addition examples. The bit level representation of 4-bit two's complement sum can be obtained by performing binary addition of the operands and truncating the bits to, yeah, so exactly what you would think. As illustrated in two's complement addition, figure 225 shows some examples where w is equal to 4. Each example is labeled by the case to which it corresponds in the derivation in equation 213. Note that 2 to the 4 is equal to 16, hence negative overflow yields a result 16 more than the integer sum, and positive overflow yields a result 16 less. We include bit level representations of the operands and the result. Observe that the result can be obtained by performing binary addition on the operands and truncating the result to 4 bits. Figure 226 illustrates two's complement addition for word size w is equal to 4. The operands are in between -8 and 7. When x plus y is less than -8, two's complement addition has a negative overflow, causing the sum to be incremented by 16. When -8 is less than or equal to x plus y is equal to 8, the addition yields just x plus y. When x plus y is greater than or equal to 8, the addition has a positive overflow, causing the sum to be decremented by 16. Each of these three ranges forms a sloping plane in the figure. So that's figure 225. Okay. This is 226 that they're talking about here, which is this one here. So you have the negative overflow, your normal addition, and then your positive overflow. Why does it say 2 here? What is that? Why does it say 2? 2's complement? Negative? It shouldn't be negative. Seems like a printing mistake. Oh. Okay, I'll come to that later. Alright, let's go to the principal equation. 213 also lets us identify the cases where overflow has occurred. Okay, detecting overflow in 2's complement addition for x and y in the range t min is less than xy is less than t max, let s equal to, okay, that. Then the computation of s has a positive overflow if and only if x is greater than 0 and y is greater than 0, but s is less than or equal to 0. Yeah, I mean that's how that works. Computation has a negative overflow if and only if x is less than 0 and y is less than 0, but s is greater than or equal to 0. That makes sense. Yeah. Figure 2.25 shows several illustrations of this principle for w is equal to 4. The first entry shows a case of negative overflow where 2 negative numbers sum to a positive one. Final entry shows a case of positive overflow where 2 positive numbers sum to a negative one. 2's complement addition, 4-bit word size. This can have a negative overflow when x plus y is less than negative 8, and positive overflow when x plus y is greater than or equal to 8. Detection of overflow, 2's complement addition, derivation. I'm not going to worry about that. Okay, let's go over here. Let's see to enter our, what are we into here? Chapter 2, Vim problems. Go down to the bottom, start a new one, 2.29. And then in here, fill in the following table. Yay, another table. Let's get our table generator. Okay, this table is going to be what? 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, 5 by 11. So let's go to table, set size 5 by 11. That's us. Okay. Sorry, my phone's been blowing up here the past couple seconds. Give me 1 second. Alright. I turned my phone off. People are just blowing up my stuff. Alright, so we're doing our practice problem here. Let's go ahead and fill in our table header. So it's going to be x, y. This is going to be x plus y. This is going to be x plus y. Say t. And then case. And then over here, we're going to have what? Just a bunch of numbers. Okay, let's go up here. And actually this row is completely empty. Not sure how that works. How do you have a completely empty row and then numbers below it? Not sure how that works, but we'll find out here. 1 0 1 0 0 and then 1 0 0 0 1. We got 4 over here, so you go down here to 1 1 0 0 0 and 0 1 0 0 0. Okay, let's go over here. 1 2 3. We got 3 more, so it's 1 0 1 1 1, and actually I fucked this up. Copying this stuff is so annoying. So you got 1 0 1 0 0, 1 0 0 0 1, 1 1 0 0 0, and then 1 1 0 0 0. So this one is wrong. So it's going to be 1 1 0 0 0. Okay, next one is going to be 1 0 1 1 1. Yep. And 0 1 0 0 0. Next one is going to be 0 0 0 1 0 and 0 0 1 0 1. And then finally 0 1 1 0 0 and 0 0 1 0 0. Bam. Okay. So the problem as stated. Now that I got my table, I'll do my generate, copy to clipboard, paste it in here. We're ready to roll. Okay. Fill in the following table in the style of figure 225. Okay. Give the integer values of the 5-bit arguments, the values of both their integer and 2's complement sums, the bit level representations of the 2's complement sum, and the case from the derivation in equation 213. Okay, so we can close this out now. Go back over here. So this table that they're referencing here is this one here. We have negative 8, sorry, negative 5. So you have the binary representations, the decimal representations, and what case it falls under. So let's go ahead and just convert these things to, I'm not even gonna waste my time doing this stuff. It's not super important for me to do this. 1 0 1 1 1 0 0. Okay, whatever. It's gonna fail because it doesn't know how to do 2's complement. Okay, so we got, what's this? 1 2 4 8 16. So it's negative 16. These are gonna be negative. So I'll just throw a negative on these because we know it's negative already. Same thing with this. Same thing with this. Same thing with this. Same thing with this. Okay, so 16, and this is going to be 1 2 4. So plus 4 would be negative 12. So you can space that out there. There's going to be 16 plus 1, which would be negative 15. Let's space it out a little bit like that. Yeah, I think we're probably gonna have to do that. Yeah. So it's gonna be 16 minus 8, which is gonna be negative 8. This is gonna be same thing. Then this is gonna be 16. This is 4 5 6 7. So 16, negative 16 plus 7 would be negative 9. And this will be just 8. It's not negative. This would be 8 here. Yeah. Bam. This would be 1 and 4, which would be 5. So just put a 5 here, put an 8 here. And then this would be 2. And then I think I can space it like this. Let's space it like this. Keep it consistent. Okay. Then over here, we got 1, 2, 4, 8. 4 and 8 is 12. 12. 1, 2, 4. This would be just 4. Okay. So we do an x plus y, which can exceed the bounds. 5-bit integer, -16. Oh, these go 4 into 5 for x plus y. The bit level representation of 4-bit 2's complement sum can be obtained by performing binary addition on the operands and truncating the resulting bit. So these are 5-bit arguments now. Okay. So let's do the sum, which is going to be 6 bits. 1, 2, 3, 4, 5, 6. So it's going to go all the way to there. 1, 2, 3. We got to add 3 to these. And then I'll do 1, 2, and 3 here. 1, 2, 3. There we go. So in here, just do our addition here. So 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 1 is 0. Carry the 1. So this would be 32, -32, and then 5 from 32 would be 30, 27, -27. All right, we can verify that here. Oops, 27. Yeah, it's exactly -27. Okay, so then the actual binary value coming out of this would be 00101, which would be negative underflow. I call it underflow, but they call it negative overflow. I guess it's overflow because the bit is overflowing with a negative value. Okay, so we're going to go positive on this guy, and it would be what case? There's a little case thing here. Case 1. So it's going to be case 1. And then up here we can represent that as just 4, 5. Yeah. So we go to 5. So let's just check that we got that one right before we move on to the next ones. So this is going to be 229. We got 12, 15, 27, 5, 1. Yep. And then the binary representations look correct to me. Okay, great. Great. That's pretty simple. So let's do the math here. So it's going to be 0, 0, 0, 0. And then this would be carry the 1. So you have 1, 1, 1. So it'd be a 1 here and a 1 here. And then that is going to be equal to 32 and 16, which would be 8, 48, negative 48. I think that's right, negative 48. Because you got 1, 2, 4, 8, 16, 32. So 32 and 16 negative values. Oh no, this is a 16 positive value, my bad. So it's a negative 32, positive 16, which would be negative 16. Yeah, which is exactly right from looking at the decimal values over here. We then take that value over here, we just pop it in 1, 0, 0, 0, 0, in which case it's still negative. We lost our negative bit over here though, and we just have negative 16 still. That's interesting, because we did what do they call this, a sign extension. That's basically a sign extension. So what case is that where our addition, it didn't fit into the space, but the space was not necessary to preserve the value? It's a good question. These are good edge boundaries. So if you look at the diagram that they have here, negative 2 to the w minus 1. So w is what, 5? So it'd be w minus 1 would be 4. 2 to the w minus 4 would be 2 to the 1 would be 2. 2 squared would be 4. 3 would be 8, 16. So it's negative 16. So it is in the range. Yep, it's in the range. That's normal. I guess you would say it's case 2. It's a normal conversion, but it's negative. So it's in case 2. That is an interesting one, because you would think dropping bits would, like, you know, change the value, but because it's a sign extension, effectively you're undoing the sign extension. Let's go ahead and check that result. What do we got here? Negative 8, negative 16, 16, 2. Yep. And then I'm not going to check the binary values. All right, so let's do the same thing over here. We got 1, 1, 1, 1, 1, 0. Yeah, because we got 1, 1, 1, 1, 1. Yeah. Yep. Okay, so that's going to be a positive value, oddly enough, because negative 9 plus 8 should be negative 1. We should get sign extension here, but there is no carry. That's the tricky bit. If we got sign extension, we would get negative 1, and negative 1 is the correct value looking at the decimal. So it seems like you have to do sign extension instead of just using the carry, because there's no carry here. It's 0 and 1, which would just be 1. But we have to sign extend to 5 bits. So that's negative 1. Then that results in just 1, 1, 1, 1, 1, which in 2's complement. Oh no, this isn't negative 1. What am I talking about? 2's complement would be negative 1. I'm trying to think through here. Okay, I think it is still sign extension. Then this becomes negative 1 still. In which case we're within the ranges. There's nothing underflowing or overflowing here. So I'm going to say it is case 2 still. So this one's a tricky one. I didn't really anticipate this being weird like this. 9, 8, negative 1, negative 1, 2. Yeah. So you do sign extension on it. Okay. That isn't immediately obvious to me that you would need to do that. Okay, so let's go ahead and replace this with 1. So that's 1, 1, and then a bunch of zeros. That doesn't make sense. So you have 1 there, you have 1 there, and then you have a 1 there. So you need another 1 here. Okay, so that's going to be 8, or 7, sorry. 7. And then if you drop the last bits, you just get 0, 0, 1, 1, 1. In which case you have 7 still. 7. So this is a positive case. If you go back here, case 3. Let's go ahead and check our results. 25773. 25773, yep. Okay, let's do the binary addition on this. So 0 and 0 is 0. 0 and 0 is 0. 1 and 1 is 0, carry the 1. 1, 0, and 1 is 0, carry the 1. 0 and 0 is that, okay. And then you have to do a sign extension. So that would be 0, 1, 2, 4, 16. Sorry, am I doing this wrong? 1, 2, 4, 8, 16, 32. Okay. So you got negative 32, so that'd be negative 16. Looks like that is what's going on here. So 12, that'd be positive 16, which would overflow to negative 16. So yeah, if we look at our diagram, we have positive 16, and then we subtract out 32, which gives us down to negative 16. And then the truncation here is going to be 1, 0, 0, 0, 0, which if we look here, 16, blah, blah, blah. So this will be negative 16 still. Negative 16. I believe that's correct. And that would be case where we overflow positively. Case 4. Okay, if we look back over to here to 229. So it's 12, 14, 16, negative 16, 4. So I guess we didn't do a sign extension here. But we did here. I guess that's where I'm kind of wondering, like, why is it that we did a sign extension here, but not here? I guess because there was no sign bit here, whereas these had sign bits set, so we sign extended it. Interesting. Well, I can't say I fully grok that, but um, 2.20, 2.30. Oops. Okay. 2.30. Write a function with the following prototype. Boom, boom, boom. So C, prototype is int tadd, okay, where we take in int x and int y, and we have implementation, return 0 here. Okay, there we go. All right. Determine whether arguments can be added without overflow. This function should return 1 if arguments x and y can be added without causing overflow. So we have to do a if branch here. So if x and is less than 0 and y is less than 0, then we might be under the situation else if x is greater than 0 and y is greater than 0. Otherwise, you return 0. So what is the return again? Returns 1 if arguments can be added without causing overflow. This is going to be returned 1 here. So we need to do the addition. So return x plus y, and we say if that is greater than 0. And then this one will say less than 0. So here, both of our operands are negative. And so we sum them together and we say if it became positive, then we got issues. And then this one says, hey, if we're going to sum them together and both these situations, they're less than 0. Both these situations are they're greater than 0. So if you say, hey, if we add them together and it becomes less than 0, then we got a problem. We did I guess this would be going from positive to negative to case 4. And this would be case 1. If we look back at the diagram, I think that's the case. Yeah, case 1 is negative overflow. Yeah. And then this will be case 2 and 3. Okay, let's pull up the resulting answer key here. T-add OK, which is 2230. This function is a direct implementation of the rules given to determine whether or not 2's complement addition overflows. Okay, so they do the sum regardless. They don't do branching. I guess they kind of do branching. With their short circuiting. But they just do the sum and then they say x and y are both, and then x is greater. They do greater than or equal to. I don't think equal is necessary. I like mine better. But I wonder if this is can I write a test case for this? But if we just think it through, if x is less than 0 and y is less than 0, then by definition, like without any overflowing situation applied to this code, by definition, if they're both less than 0, then the result has to be less than 0 unless it overflowed. So that's what we're testing here. I guess you would say equals 2 because it could overflow into a 0. Yeah, okay. Yep, that does make sense. Yep. And then here we're going to say, hey, well, if x is greater than 0, I guess we would say greater than or equal here. And then we'll do a less than there. Yeah, okay. Okay, let's go down to 231 here. Oops. So if we look at the lectures, I'm just going to bring up the lectures real fast. Because I do want to get into the next lecture. Sorry, wrong repo. This one here. CSAPP. Our lecture, video lectures here. Lecture 3 is bit, bytes, and integers continued. So I need to get to floating point before I can consume this lecture here. So let's just look ahead a little bit. So we got some problems here. 2's complement negation is the next thing. We got a webicide, unsigned multiplication, 2's complement multiplication. Problems with that. Another side multiplying by constants. And then dividing by powers of 2, which is a right shift. And then final thoughts on integer arithmetic. And then we get into floating point. So that's 144. So we got about well, 14 pages roughly with problems to get through before we can go to the next lecture. And then that lecture will be effectively a review for me, having read the material. But I will feel like I'm ahead of lectures, which is psychologically good. All right, so your coworker gets impatient with your analysis of the overflow conditions for two's complement addition and presents you with the following implementation of T-add, okay. Determine whether arguments can be added without overflow. Warning, this code is buggy. So they just do the addition between the sums, and then we say, hey, you look at the code and laugh, explain why. That's brutal. So you do the sum, and you say, hey, if the sum minus x is equal to y, and why do I laugh? Because subtracting the operands from the result and comparing to the other operand will work even if an overflow situation occurred. Because it is modular arithmetic. And then I'll indent these because why not? Let's see what they say here. 231. Your coworker could have learned by studying section 232 that 2's complement addition forms an abelian group, and so the expression so-and-so will evaluate to y regardless of whether or not addition overflows. Yeah, they call it an abelian group, but it's basically modular arithmetic. All right, next problem is 232. And this is, you're assigned the task of writing code for a function t sub, okay. So that was t-add, okay. T sub, okay, with arguments x and y that will return 1 if computing x and y does not cause overflow. Having just written code for problem 230, you write the following, where you just negate one of the operands for for what values of x and y will this function give incorrect results? Writing a correct version of this function is left as an exercise. Well, let's see. That's a good question. I mean, it's mostly correct, but it's going to be on the extremes. So let's take the 4-bit example. Or we can just take a 2-bit. Want to just do a 2-bit? Yeah. We'll do a 3-bit. So it's probably going to be the extremes where one of the operands is like so 3 bits represented you could have negative, we'll do 3-bit values, have t values, we'll say t values, and we'll have negative or t min. 3 is equal to 1 0 0, which is equal to obviously that's a binary. 1 2 4 negative 4. 1 1 1 would be negative 1. T max would be 0, 1, 1, which would be 3. So say in this situation you pass in 1 and 1 turn into 1 and -1, which then have the operations performed on them, in which case 2 will pop out. And we'll do these as binary. So these are just some test cases. 0, 0, 1, 0, 0, 1. So this turns into 0, 0, 1 and -1, which would be 1, 1, 1. In which case we add together 1 and 1 would be so 1 and 1. 1 and 1 would be 0, carry, 0, carry, 0, carry. And that'd be 0. So that's correct. Let's do some of the extremes, like let's do like 0 and 3. So that would be 0 and 3 here. And if we do the negation of 3, so that'd be 0 and 3 negated would be 1, 0, 1, because it would be 4 plus 1, yeah. And then if we do the arithmetic here to add things together, we get 1, 0, 1, which is -3. Yeah, that's correct. So say we say a -4 and a -3, or -4 and 3. So -4 is going to be 1, 0, 0, 3 is going to be that. This will be 1, 0, 0, 3 is going to be that. And then we add them together, we get what? I don't want to assume correctness here. 1 and 1 is 1, 0 and 0 is 0, 1 and 1 is 0, carry the 1, truncate it, we get 1. Which numerically is not correct, but it might be the correct I think it has to do with the negation. I guess we have to run these values through t at OK. So it's going to be negative and a negative. So that's going to be this case. Correct. That's correct. My guess is when the right-hand operand is negative. Yeah. Let's do that. So we got 3 here, and then we go -4. It says, for what values of x and y will this function give incorrect results? Writing a correct version of this function is left as an exercise. So I'm going to do 0 here and say -4. So that's going to be 0. -4 will be 1, 0, 0. Converting this to 4 is going to be tricky, because what we do is we negate everything, which would be 0, 1, 1, and then we add 1 here. Wait a minute, 1, 2, 4. So you'd have negated plus, this would be 1, 0, 0. Wait a minute, that's wrong. Yeah, because there is no +4 representation. When you negate t min, you get back t min. because it becomes 0, 1, 1 here. And then you add the 1, it becomes Tmin again. And then when you add those two values together, so they're going in positive now. So that's going to be incorrect. Oops. So if you add these two together now, it comes out as -4, which is 1, 0, 0. Which, what's going on here? Oh, because I put the negative here. Okay. Let's do that. There we go. Because we had 0 and -4 go in to our function. We then converted them into what should have been 0 and +4, but it came out as 0 and -4 still. And then when we came out, we have -4. What we wanted is +4. Basically, we can't represent. So the case where where y is t min, because when you negate the operand, it returns the same value. Oops. And then I can demonstrate that here with clang REPL. So clang REPL, REPL, and then I'm gonna do pound include standard io.h, and then here we're just gonna do this expression printf, and I'll just give it the numeric value. What we're gonna say is x, and that's gonna fail because x is undefined. But we can say char, we say unsigned or signed char x is equal to 0x 80. So now when we print that out, that's going to be its maximum value. And now if I negate it, huh. $80 is not a negative value. I think what happened is I negated the char and it got converted into a. I think what I need to do is say, hey, you're still a char after this process. Yeah, okay, there we go. So x and -x are both the same value, same bit pattern. Yeah, what happened there is that the negative here converted this into like an integer or something, or short or something large enough to fit the result. Okay, I think, well, I identified one value of y here, because when you negate it, it becomes itself, and then that causes problems. But only because we had incorrect operands going in here. I think because the result is going to be, so if you have a negative, and if you have 0 and you have a negative going in here, we're going to say, hey, that's a normal result. And it'll come out as -4. So 0, it can't be 0 here. We need something that would actually screw up. So like a -1 here. So let's do that. So -1 would be 111. And this would still be 111, and that would still be that. And then the result would be 1 1 0 1. So 1, 1, 1, 1, 0, carry the 1, and then we drop the 1 here. So the result would be, the result that we're looking for is a positive 3. So that's the correct result, but would it be able to detect it? Sorry, the correct result would be, yeah, positive 3, because this is going to be a 4. Minus 1 would be 3. So the sum is the same, but is it able to detect that it underflowed? Because this did underflow. Let's look at the arguments that go into it are the same exact arguments. So x is going to be less than what? I think it still detects it, right? I don't know. This is tricky. I'm gonna have to write some code for this. Okay, so let's hit Control-Z. I'm gonna copy this code here, and we're just gonna write some code here and say vim test overflow detection .c pound include standard io.h standard lib and main, and we'll do some semicolons here, bam, and then the implementation here of, what was this, t sub okay, sub okay, int x and y, and we're just going to return t add okay x negative y for all 32-bit integers. I guess you can do 8-bit. Let's do 8-bit. Let's not do everything. Note buggy implementation from the book. Okay. For auto I, we say char I, char, and we're not gonna do ints here, we're gonna do chars. Int, sorry, int, just to make it, actually we'll do signed chars, just to make sure it's signed char. Can I just do a void here? Just delete all that. Alright, for signed char I is equal to 0. Actually, I want to say 0x 80. I is less than 0x what would this be? The last bit of a nibble not being there would be 7. Shit. 7 FF? Yeah, because you'd have 4, 5, 6, 7 F. While I is less than 7 F. plus plus I. Then we do the same thing with J. We just do X and Y here. Keep it consistent. X, Y. Can we just do like a printf of %d, new line, and we'll do X and Y here, X and Y, and then oops, got plenty of things here. Main rest return int. Okay. What was this complaining about? Okay, it's always going to be true because X is a signed char and this is unsigned. Okay, that makes sense. Can I just say signed char here and then say signed char here? Make build test. What am I testing here? Overflow detection. Negative 128 goes all the way to, okay. Got to 114. Oh, yeah. Let me launch the 2's complement calculator. And we're going to grab 8-bit value. I'm going to say in binary. Enter binary value will be 0, 1, 2, 3, 1, 2, 3, 4, which should be, oh, it's not 8F, it's 7F. I thought I put 7 there. Alright, make, rerun, and then less than or equal. Yep. Oops. I'm just going to quit out of that. Alright. Vim test overflow detection. This will be less than or equal. Make. There we go. Oh. So that goes forever. That's not right. Yeah, because this plus plus will just wrap it around. That makes sense. What we want to do is visit every possible value for both x and y to generate a table. So we initialize it to be the most negative, and then we go all the way up to, but not including, the most positive. So we need a test here, which says x. Let's do just some bools here. Bool x is equal to y, which is equal to false. I think I can say it like this, right? well, I know I can do it like this, bool x and bool y. And we'll say x start. Y start. Here we'll just say x has started incrementing. We'll do it at the end here, which means that we should probably put some braces around this. Same thing for this. I think we're at that point where we could use some braces. So here, we're just going to say, actually, I think we can get away with saying x start plus plus as well. I don't want plus plus, I want it. X start is equal to 1. Y start is equal to 1. So now we can do away with these braces. And I guess we say true here. True. Okay, and our condition here is say, okay, you're going to be less than or equal to that and not x start and not y start. Okay, I think that effectively gets us what we want. Make This is where it's starting to get a little bit confusing. So you have the condition where x is equal to y, but we want to make sure that we're also, if x is equal to and some condition involving x start, so x is equal to 0x80 and we can just do this as an if to simplify this. Say here if x is equal okay, that looks right to me. Oh, but this needs to be a sign char. No. This needs to be a sign char. Okay. Make. Okay, that worked. So negative 128. Wait a minute. It just did 1. We did all the way up to positive 127, and then it just died. So this break worked. So the first iteration of this, I would think oh wow. Oh, because it's not reset, that's why. So here, Y start is shared. What we need to say is Y, or sorry, in this case it'd be X, bool X start is equal to false. And then this needs to be bool Y start is equal to false. Oh, and we need to do a semicolon here, or sorry, comma instead of a semicolon. There we go. Expected bool. I'm declaring it here though. Book. Huh. Why is this? I guess you can't declare inside the block. Okay. Okay, what we need to do is when we break, so we're done with Y, we need to say, hey, Y start is equal to false, because we're just about to break. And technically we should break, we should set Y X start here as well. But we're breaking out, so it doesn't matter. And then I'm just gonna delete these printf since they're not needed. Make. There we go. That's every permutation of every value. So it should be 256 times 256. 256 times 256. Not implemented yet. Oh, I gotta do printf. 256 times 256. So that's what I should get for my word count. 60536. Yep. Okay. All right. So we have a way of iterating over every single value for both X and Y on an 8-bit integer. But now we need to call, instead of printing, we need to call our, well, we'll do a printf as well, but we're going to call what I'll do is I'll say t add okay of those two values. returns %d here. So here will be t add okay of x and y. Oops, didn't want to do word count, I want to do less. I mean, that's a lot of results. All right, I'm gonna go take a bio break real quick, and I'll be back to work on this. I think I'm getting a little bit caught up on this, so the problem is like I can't write the test cases for 65,000 some odd. It's basically 2 to the power of 16 different results to assert whether they underflowed or overflowed. That's what we get with 2 8-bit integers. And there's no such thing as like a 3-bit integer in C as far as I know. Let's see, let's ask AI. All right, let's try it with a 3-bit. So we're going to simulate a 3-bit here. No, we can't do that. Okay. I feel like I'm wasting time on this. I'm not going to crack this, just brute force. So let's take a different approach. Let's go back to just an analytical approach. So where we're doing a 3-bit permutation, let's do a 2-bit. 2-bit t values. So in this situation, we have t min of 2 will be this, and that will be a -2. Sorry, because 3 times 2, that'd be 6 bits. 2 to the power 6 would be 2, 4, 8, 16, 32. It'd be 32 different values. If we go down to 2 bits, it's just 4, which is 2. But there isn't I think it has to be 3. Let's just do 3. Okay, and we'll just generate a whole table here. So we'll start with the t-min, which is 1, 0, 0, and 1, 0, 0. We then go to 1, 2, 3, and then this flips over to 0. And then we count from 1, 2, oops, 3, yeah, 1, 2, 3, 4, 5, 6, 7, 8. Yep, 8 different permutations, and we have 8 times 8. That's a lot. Why don't we just take it down by 1, which would be killing this column, killing this column, and then killing 2 values here. Okay. Next one's gonna be 1, 1, like that. Next one's gonna be 0, 0. And the next one's going to be 0, 1. Okay. So it's a little bit more manageable. T min 2. Just like that. So T max 2. 1. -2. So let's do like this. XX negative YY. Sorry, YY. We'll just do negative YY. Why not? And then that will be leading to a result. So these will be 1, 0. These will be 1, 1. This will be 0, 0. This will be, oops, 0, 1. YY, when you negate 0, you get back 0. When you negate 1, you get back a 1 here. When you negate 1, 0, the negation process is to invert all the bits and then add 1. Invert all the bits and then add 1. That works for both of those. Invert all the bits and add 1. So it'd be 0, 1, and then you add 1, which would be 1, 0. And then invert all the bits here, which would be 1, 0, so it'd be 1, 1. So let's go ahead and copy these down to here. Oops. Let's do that again here. And here. Okay, so this is supposed to be I'm going to add some parentheses here. And same thing here. To make it obvious what's going on here. So 10 is going to be a, and we just do the entire table here. 1, 0, 1, 1, negative 1, and then you have 0, 0, which is going to be 0 obviously, and 1. So 1, 0 would be negative 2 and negative 2. So all of these are going to be negative 2. Negative 2. These are going to be negative 1. These are going to be 0. And these are going to be 1. So here you're going to have different values. So negative 2, 1, 1 is negative 1, 0, and 1. So I think what I need to do here is just to make things spaced evenly. Do one of those, do one of those. And now I can copy this whole column here down because these are identical values. I'll paste it there, there, there. Okay. Okay. And this is negative 2 and negative 2. We'll just put an X here because that's weird that it's not positive. It should come out 0. Here we got negative 2 and 1, which is correct. So these are all going to be negative 2 here. Negative 2. Negative 1. 0. And 1. So here, this is going to be 0. Put a space here and there. And then this is going to be negative 1. Yeah. So negative 2. So this should be 2 and 1, negative 2 and 0. Yeah, so the rest of these are okay. Does that pattern persist? Yeah, it does. So we'll take all of these, paste them there. Oops, paste them there. Okay. Paste them there. Paste them there. So these are the weird ones where negative 2 came out. It should have been a positive 2. X, X. The rest of them negated correctly. So basically, it was that case where, like I said, where originally that the y value is weird. So I think these are the main cases here. So I'm going to take those. So when we go into add OK with these values, we're both negative. But this is supposed to be a positive too, in which case it wouldn't overflow. Should not overflow. But because they're both negative, when they get added together, but do. So -1 and -2 should be +1, or sorry, -1 and, wait a minute. Wait a minute. This should overflow. I guess the problem I'm running into is like the detection logic relies on I guess it's good detection logic, but I guess, you know, I'm just gonna say when y is equal to when y is equal to t min, things get weird. I'm just gonna say, I'm gonna move on from this because this is taking too long. 232. The function will give correct values except for when y is t min. Yeah. In this case, we will have -y, which also equals t min. And so the call to function t add OK will indicate overflow when x is negative and no overflow when x is non-negative. In fact, the opposite is true. T sub OK should yield 0 when x is negative and 1 when x is non-negative. One lesson to learn from this exercise is that t min should be included as one of the cases in any test procedure or function. Yeah. All right, let's move on. 2.33. Let's go ahead and kill that. Okay, 232 we just finished. Let's read a little bit about this 2's complement negation. We can see that every number x in the range t min is less than x, is less than t max, has an additive inverse under addition, 2's complement addition, with which we denote the negative as follows: principle of 2's complement negation. For x in the range of so and so, its 2's complement negation is given by the formula so and so. Basically, when x is t min, then it's equal to t min. Otherwise, it's equal to its negation if it's greater than t min. That is, for w-bit 2's complement addition, t min is its own additive inverse, while any other value x has negative x as additive inverse. 2's complement negation, observe that, okay, I don't need a derivation. Practice problem. We can represent a bit pattern of length w is equal to 4 with a single hex digit. For a 2's complement interpretation of these digits, fill in the following table. Determine the additive inverse of the digits shown. Okay. Another table. Bust out our table generator. All right, this table is going to be 1, 2, 3, 4, 5, 6, 7, 4 by 7. And then, come on, we'll just say x and negative x. Then here is going to be hex, decimal, hex, decimal. Then here we have 2. This is all blank. We have 3. We have 9. Oops. We have B. We have C. 239 BC. 239 BC. Generate. Copy to clipboard. Paste. Okay, there we go. And then, wait a minute. Yeah, this needs to pop up here. Something like that. Okay. And then these we can space in here. Okay, decimal. Well, 2, 3, 9. B is going to be 11. Should be over there, so I'm going to space these in. And then C, 12. Negative X. Oh, we forgot to switch these. Decimal to hex. Yeah, -2. I mean, none of these are extreme values, so they're just the negation, right? We can represent a bit pattern of length W is equal to 4 in a single hex digit. For a 2's complement interpretation of these digits, fill in the following table in to determine the additive inverses of the digits shown. None of these are F or 8. Oh, but they are negative. If you had 8, then that would be a problem. But none of these do have 8. I mean, we can't say like negative B. We can say negative 11, negative 12. So -2 is going to be -8 minus or plus 6, and that'd be 1, 1 here. So that'd be 8 minus 6 negative, yeah. So now, what is that? That is E. And then this is going to be -3, which is -8 plus 5, which would be 4, 5, which is going to be what? D, E, that makes sense. Then F would be its own inverse. No, F is not its own. F would be the inverse of 1. 8 would be its own inverse. Alright, -9 would be -8. Wait, you can't get to -9. Maybe that's where this thing starts getting tricky. So -8 is the maximum value. Oh, so these are negative values. I need to correct these. It's my bad, my bad. So 9 would be 8, like that. And that would be -8 and a +1. So that'd be -7 here. In which case +7 would be its inverse. and positive 7 would be 0, 1, 1, 1, which would be 7. 7. Okay, I'm going to delete these since they're not needed anymore. Alright, B is going to be what? 10, 11, I think? Because 10, 10 is A, 10, 11. Yeah, it's B. So its numerical representation would be negative for sure. And it'd be negative 8 plus 3, which would be negative 5. So its decimal inverse would be 5. And that would be represented as 5. And then over here, C would be what? 10 or 11, 10, 11, 0, which would be a negative 8 plus 4, which would be negative 4. So its inverse would be 4, which would just be 4. So I think that's correct. Let's check it out. 233 here. So we got 2, 2, negative 2e. Yep. 3, 3, negative 3d. 9, negative 9, negative 9. Wait a minute. Messed that one up. I did get the hex correct. But why is the decimal... I don't think that's correct. I don't think that's correct in the book. So this intermediate, these values here, I got everything right except for 9, which it says is negative 9 for its decimal. That's just not the case. Because if you look at the representation of 9, it's 1 in the 8s and 1 in the 1s. So that's 9 there. So it'd be negative, wait a minute. Oh, they're just saying bit patterns. They're using hex as bit patterns. So in this case, it'd be 1 and 8 and 1 here. That'd be 9. Converting that to decimal, though, is negative 7. Yeah, that's correct. So they have negative 9. You can't represent negative 9. How does that even... I'm rolling with my value because these dudes are smoking something. And then they wanted us to comment on something here, something else, right? What do you observe about the bit patterns generated in 2's complement unsigned? Problem 228. Negation. I don't care about that. Okay. Now we have a website. Okay. So let's open up here. We go CS app, websites. This is for data T negation. How many pages is this bad boy? There's a couple. Okay. Okay. What we got going on here? Data team and aside problems. This would be Vim. Data. What was this thing called? Tneg. Okay. All right, after we get through this negation webaside, there's multiplication for unsigned and two's complement. And then a bunch of problems. And then we have a little aside, and then multiplying by constants. Dividing by powers of 2. And then more on integer arithmetic. I think what I'll do is I'm going to watch the lecture now because I'm losing motivation on this thing. Yeah, let's watch the lecture now. Let's open up the web. What is this? I just go to GitHub. Video lectures. This one here.
And
I'll do it on 1.5x. Alright, I'm gonna go grab something to drink while I watch this. Be right back. get this lecture going.
The rest of the staff request is that you, whenever you have a question, you first read the book, and then you reread the assignment, and you maybe reread it again, and then you ask us. Because a lot of the questions we're getting are ones where we just say, look at this page of the book, look at this paragraph of the assignment, look at this part of the file that you were given. And so, I mean, there's a lot of stuff, and I understand how sometimes it's easy to miss things. So I'm not saying don't ever ask questions, but just before you ask a question, try and figure out, have I really sort of come through the resources I have available to see if the answer to my question can be found there. So anyways, enjoy the lab. So today is a sort of second part of a two-part lecture on integers and integer arithmetic. Last time we looked at representations about how bit patterns can be interpreted as either unsigned numbers, meaning they range between 0 and 2 to the word size minus 1, or as 2's complement numbers, which is the most usual way to represent what are sometimes called signed numbers, ones that can be either negative or positive. And by the way, there are other ways to represent signed numbers out there, but 2's complement is so overwhelmingly the most used system that that's what we concentrate on. Today what we'll do is now go beyond the representations of these values to talk about arithmetic operations on them and some of their properties. And what we'll do in general is talk about the unsigned case, which is in some ways easier to understand and more intuitive, and then talk about the 2's complement case. So the basic rule on this is if you take two numbers that range between up to the maximum value of an unsigned number and you add them, then in principle you might need to get an extra bit to represent that sum if you want to represent the true sum, the sort of integer sum of those two numbers, because you're doubling it. And unfortunately, we can't just go out and add more bits to your computer indefinitely. So we just stop it at some point and say, well, whatever bit happened to be in that sort of next over bit position, we're just going to drop it and pretend it doesn't exist, and say that the result of addition is just whatever the W bit pattern you get if you only consider the first W bits out of it, with no warning, no messages, no error or anything. This is just, it happens silently. So for 2's complement, this is not such a hard thing to understand. It can be thought of as just modular arithmetic, computing modulo the 2 to the word size. So I'm going to use some examples, and this time I've got them worked out a little more carefully so I won't get mixed up as much. And we'll use a word size of 4 here. And as I mentioned last time, it really helps with this to do the examples with small word sizes to get your intuition for it, rather than trying to write out 32-bit numbers or 64-bit numbers or something like that. So if you think about in the unsigned case, a 4-bit number means that it will range between 0 and 2 to the 4th minus 1 or 15, right? And so let's just do a few examples of cases where it overflows. So if you add 13 to 5, first of all, you know, I assume already, that you just add binary numbers the way you learned in school, just doing carries and so forth, except it's all modulo 2. So this is 0 carry 1, 1, 0 carry 1, 0 carry 1. So in principle, to represent the sum, which is, this is 5, so to represent 18, you need 5 bits, not 4. But we're just going to conveniently drop that number and say that this is actually 2, which of course is what 18 modulo 16 is. So the unsigned case is really pretty straightforward. And we can visualize this, and this picture is in the book too, by saying if you were representing on the x and y axis what they call u and v are values between 0 and 15, the range of possible unsigned numbers. And if we were to add those, we could get a sum that's up to as much as 30, which would in principle require 5 bits to represent. But what we'll do is we'll just, by dropping that most significant bit, what we do is sort of create a cliff that when you roll over from 15 to 16, instead it drops all the way down to 0. And that's referred to as an overflow. And then from there, we'll build up to the maximum value here will be 14, which is 30 minus 16. So what we've done is basically, as this picture shows, when we overflow, we effectively subtract off 2 to the w from the sum and keep it within the representable range of w-bit numbers. So that's unsigned. 2's complement, the first thing I want to convince you of is that 2's complement addition looks just like regular addition. In other words, I can perform subtraction, an addition of subtraction of numbers by using this 2's complement representation for negative numbers. So let me just show you some examples of that. So first of all, remember that what range of values, what's the smallest number that could be represented with a 4-bit, the most negative number, 4-bit 2's complement number?
1, 0, 0,
minus 8. And the largest? Plus 7, thank you.
0, 1,
So let's just do some examples. If we took this number 1101 as a 2's complement number is -3. And we add it to 5, we'll get what we got before. And we're going to ignore whatever carry bit it is, and so the result is 2. And lo and behold, that's what 5 minus 3 is. So it seems like magic because it is. And that's why part of the reason why 2's complement is sort of the most commonly used way of representing signed numbers, because the same hardware, the same algorithms that are used for doing addition works for either unsigned or 2's complement numbers. This works as well just to show you if the overflow goes, if the resulting sum goes the other way. So if I have -3 and -5 and +3, and I add those together, I'll get 1110, which is -2. So again, if you use the same patterns for the same rule for addition as you do with unsigned case, you'll get 2's complement arithmetic. So let's look at a few cases where the 2's complement overflows. So if we take 3 and it's -6, and we add them together, we'll get 1, 1, 1, 0. We're going to drop off the carry, which is what? 7? So we've added 2 negative numbers, and it's become positive, and that's referred to as a negative overflow. And the reason, of course, is the number -9 can't be represented in a 4-bit 2's complement number. So it overflowed. You'll notice that the +7, of course, differs from -9 by 16, and that's not an accident. And then going the other direction, if we had 2 large positive numbers, so if we had 7 and 5, we'll get -6. So this was 7 plus 5 is -4. And so this is referred to as positive overflow. We've taken 2 positive numbers and added them together and gotten a negative result. And you can see this, by the way, if you think about this addition. We took 7 and 5 would be 12, and this is the bit level representation of 12. It's just that because this is now the sign bit, we think of that as -4, not positive 12. And so that's the idea of 2's complement overflow. And you can see there's 2 different cases here. One is where the number that the sum was, if we looked at the true sum, the number that you get, for example, 12, is too big to represent. And so when we think of that as a 2's complement number, it becomes now a negative number. So that's positive overflow. Similarly, if we have 2 negative numbers and we add them together so that the sum is too small, too negative to represent, then those become positive numbers. That's negative overflow. And you can see that in this picture, the same idea as before, except there's 3 regions. This is the, and by the way, now you'll see our numbers range between -8 and +7. And the sum, 2's complement, will also range between -8 and +7. But there's these 3 regions. One is where everything's fine. It's within the representable range. The other is where the sum was so far toward the negative side that it becomes positive, or where it's so high on the positive side that it becomes negative. And so part of data lab, you'll learn to understand these quite precisely. But that's the idea, and it's a little bit counterintuitive to say, somehow I can accept the idea that modular arithmetic for unsigned numbers, there's some sort of mathematical beauty to modular arithmetic. And this just looks like kind of useless, right, from a operational characteristic. But it's the way it is, and we're stuck with it. And multiplication is basically the same idea. In fact, all the operations are basically the same idea, that if you can't represent it within the word size, you just take the lower W bits. So all this complicated notation here is just a way of saying, in principle, if you take 2 W bit numbers and multiply them together, you may need the result may require as much as 2 times W bits to represent. Before addition, it's W plus 1. Multiplication, you actually have to double because you're potentially squaring the largest number. And so again, we don't want to just keep doubling our word size over and over again. We'll run out of bits very quickly that way. And so we just truncate it at W bits. And for the unsigned case, it's, again, modular arithmetic. It's something that you can kind of understand and believe. But for and so, again, let's just do a few examples. And I won't try and work out multiplying in binary is like multiplying in decimal. You do a big table, and it takes a long time. So I won't try to do that. But let me just show a few examples. So if I multiply 3 times 5 is, of course, equal to 15. And in an unsigned number, I can represent that. Right? So that's OK. But if I multiply 5 times 5, then that would have a representation. If I were to think about it as possibly as many as 8 bits, it would have a representation with an extra bit. And I'm going to throw this part away. And so I'd call that 9, which, of course, is equal to 25 mod 16. And so that's the general idea of it, is regardless of whatever is in this upper part of the word, the product, I'm just going to discard that and only look at the lower one. And life gets a little more interesting with the 2's complement case. So let's look at what that does. And the answer is even a little bit stranger in that you not only throw away whatever high order bits happen to be there, but whatever bit gets left in this position will determine whether it's a positive or a negative result, even though with completely irrespective of the signs of the original 2 operands. So that can make you go all over the place. So if we had 5 times 4, or 20, that would be represented in this 8-bit form like so. And we'd just call that 4, right? Because we're throwing this away. But if we did 5 times 5, as we saw before, that's represented like this. And that's now becomes, so we're throwing away this, and this becomes our sign bit. So the result is a -8 plus 1, or -7. So you see, this is similar to an example we showed at the beginning of the first lecture, that you can have 2 positive numbers and multiply them and get a negative result. And because of the sort of quirks of this overflow. Question there? Oh, I'm just taking 25 and writing it in binary. Yeah, if you want to. You know, you start with the 2 numbers. I'm not going to do it. Well, actually, this one's an easy one. There's a trick for this. If you want to multiply a number by a power of 2, we're going to show that later. You just shift it left by 2 positions. So that one's an easy one. Otherwise, you have to write out the table and sum all the results and all that stuff. I prefer to let computers do that. And again, this 2's complement stuff, one interesting feature is that it works for negative numbers, too, if you do this trick of throwing away the high order bits. And you'll have overflow cases like before, because you're throwing away information. But the lower bits, if the number is representable, you'll get the right result. So let me just demonstrate that to you. So this is -3. But you remember that this is equivalent to 13 as an unsigned number. And this is -2, which is equivalent to 14 as an unsigned number. So now if we multiply 13 times 14, you get 182. And that has a
I'll hop back on a little little bit. I have to do something.